Okay, so today we're going to start chapter 10 on mathematical induction. So this is a very, very powerful technique to prove kind of a specific type of theorem. The theorems that work, that proof by induction works well on, are statements that claim something is true for all natural numbers. Like, for any natural number, this equation is always true. So for any natural number n, its inequality is always true, involving n. So those are the type of statements that we're going to prove using mathematical induction. Okay? So I'm teaching Math2200 class, and it's a problem-solving class. And one of the questions is that I had my students answer was, add up the first 1,000 odd numbers. Okay, so I just want to let them sit there for the rest of the semester counting.
Oh yeah, we had a
So
this morning.
there's a really bad way to do that. Sit here and add 1 plus 3 plus 5 and just do that. I mean, it take too long. You can mess up. Or there's kind of a clever way to do it, and it starts with if you look at let's look at some sums of odd numbers. So here's the question. So find the sum of the first, say, 100 odd, or let's say 1,000 odd numbers. Okay. Well, so what's hard about this is that we're asking for so many of them. The word 1,000, the number 1,000 is pretty big. So let's look at smaller examples. Like, the sum of the first odd number is 1. 1 plus 3, the sum of the first two odd numbers is 4. The sum of the first three odd numbers is 9. The sum of the first 4 odd numbers is 16. The sum of the first 5, hold on, some of you see patterns quickly. So the first 5 odd numbers is 25. You guys see a pattern emerging in the sum?
N squared.
Yeah, so check this out. So the sum of the first 1 is 1 squared. 4 is 2 squared. 9 is 3 squared. 16 is 4 squared. 25 is 5 squared. So it appears, so we have a conjecture. What we say a conjecture is, a possible theorem. Maybe there's a possible theorem here. I claim, it looks like, that if I add up a certain number of odd numbers, it'll always be that number squared, right? The sum of the first 5 odd numbers is 5 squared. So could it be that the sum of the first n odd numbers equals n squared? So that's kind of what we call a conjecture. It's like a hypothesis. I think it's true. And just you can do several more examples and kind of convince yourself it is true. So that's actually the fast way to add up the first 1,000 odd integers. So what's the sum of the first 1,000 odd integers? It would be 1,000 squared.
What is that, a billion?
So if you have 1 with 3 zeros times 1 with 3 zeros, you get a 1 with 6 zeros. So it's 1 million. So it's kind of interesting, huh? Did I just prove this statement? Is this a proof? Look, I did 5 examples. I mean, that's got to be a proof, right? So, think about chapter 9, counterexamples. One counterexample can disprove a statement. A statement says something is true for all numbers, and you give one counterexample, that shows that it's false. But a million examples doesn't prove a theorem, but it gives you a lot of evidence that the theorem is true. And so this is way a lot of conjectures and statements in mathematics are believed to be true, even if people can't prove them yet. But they have like tons of data to confirm the hypothesis. Like one of the most famous unsolved math problems is the Riemann hypothesis. And if using computer technology, you can, the statement of the Riemann hypothesis has been confirmed for several, for case after case after case. And so there's tons of data to confirms the Riemann hypothesis, but nobody's proved it yet. So if you guys want to work on that, you can make probably at least $1 million prize for the person who solves it correctly. I'd say it's probably more like $5 or $10 million at this point.
Yeah, there's one theorem that Dr. Lee solved a couple years ago that previously went unsolved.
Yeah, and some of them, if they're the more interesting the theorem, the more useful the theorem would be. Is the more money that people kind of stake for the solution. All right. So my point is, this is like a theorem, but I haven't proved this. I mean, how would you even go about proving this? I mean, like I said, you can't just show it works for a few examples. I mean, if you took an arbitrary integer, like an arbitrary number of odd numbers, I mean, how can you, if you have like a formula involving n, how can you just automatically show that it equals n squared? Well, this is the type of theorem that you prove with induction. Okay, so statements like this, we'll actually prove this today. That the sum of the first n odd numbers actually equals n squared. We'll prove this using induction. Okay, so that's kind of a little motivation, the type of problems, type of theorems that you need to prove. So this let me list some theorems that you can prove. So for every natural number n, 1 plus 3 plus 5 plus 2n minus 1 equals n squared. So the nth odd number, you actually write it as 2n minus 1. So that's what I just wrote there, my conjecture. That's how I would write it as a theorem. For every natural number n, the sum of the first n odd numbers equals n squared. So we'll prove that using induction. So here's another example of a theorem we could prove. For every natural number n, 1 plus 2 plus 3 plus all the way to n. So here, this says the sum of the first n natural numbers, so 1 through n, add them up, what do you get? N times n plus 1 over 2. It's kind of a famous theorem. I'll explain to you why it's kind of a famous proof to this. But we'll actually prove this using induction as well. And another theorem, you can actually prove things like this. It's actually more than just for integer or for natural numbers. For any non-negative integer, so for any integer n greater than or equal to 0, 3 divides 4 to the power n minus 1. Okay. So these are the type of statements. So they're similar. It's a statement that involves a natural number. Okay? In this case, a non-negative integer. It just kind of works out trivially that when n is 0, this is a true statement. So it really is a statement about, it's a universal statement. Something's true for all natural numbers. What's true, this equation holds for all natural numbers. This is kind of like an equation too, right? If I said 3 divides 4 minus 1, we think of this as an equation. 4 minus 1 looks like 3 times an integer. Okay? So these are the type of statements we can prove with mathematical induction. All right? All right, so we'll prove these today, and maybe more if we have time.
I think another one I think student from another class had was what is the number in the one spot and like 2 to the 1,000th power?
Yeah. Yeah. So the math majors in the math theory lab confuse the heck out of my 1100 students because they try to show them sigma notation and things like this, and they're like, "What? I'm just adding up numbers." So, all right. So they just come to class to pay attention. All right. Proof by induction. So So mathematical induction and most people would just say they'll just use induction. So you can just say proof by induction. You don't have to say mathematical induction. Some books would say the principle of mathematical induction. So the principle of mathematical. So we prove this by the principle of mathematical induction. That's a lot of words. Mathematicians don't like that. So it becomes PMI. Proof by PMI. But most people, you would just say it's a proof by induction. Okay? Mathematical induction or just induction is a proof technique used to prove statements S sub n are true for all natural numbers n. Okay? So you have some statement, I'm going to call it S sub n, some statement involving an arbitrary natural number n. So we want to prove that every one of these statements is true for every natural number n. Okay, and I give you 3 examples of statements like that. So the sum of the first n integer, sum of the first n odd number equals n squared. Okay. All right. So how do you do a proof by induction? So here's the technique: proof by induction. All right. So to show S sub n is true for all natural numbers n. First, we're going to show that the statement is true in the easiest possible case. Sometimes the easiest possible case is when n equals 1. Most of the time it's when n equals 1, but I gave you an example where a statement was about the smallest n of the work was 0, n equals 0. Okay? So the first thing we're going to do is show that this is true for the smallest number in our set. So we'll just assume it's n equals 1. Okay? So first, this is called the basis step. Okay? First, the basis step. We're going to show that this statement is true when n equals 1. Usually this is a pretty easy thing to do because the statement becomes very, very trivial when n equals 1, usually. Okay? So we're going to prove that the first statement we'll call that S sub 1 is true. Okay? So whatever our theorem says, we're going to prove that the statement is true for n equals 1. Okay? Like I said, this is most of the time the basis step is very easy. Okay? Because if you have these long equations, when n is 1, it kind of collapses. You just kind of verify, like, okay, you get 1 on the left side, you get 1 on the right side. Okay, it's true for n equals 1. All right, that's the basis step. Second, this is called the inductive step. An inductive step. Okay. So for any integer, k that's greater than or equal to 1, we're going to assume that S sub k is true. Okay? So we're going to say, you'll make a statement like, well, suppose the statement is true for some positive integer k. Okay? Then we're going to use this assumption. This assumption, by the way, is called the inductive hypothesis. So you might see that if you read the book. It might say something like, well, by the inductive hypothesis, that's this assumption right here. Okay? Assume the statement is true for some k. Okay? So this is called the inductive hypothesis. Okay? Assume that Sk is true, and then we're going to show that that forces the next statement to be true. the next statement would be s sub k plus 1, the next case. Okay? So we're going to assume that sk is true and prove that this forces s sub k plus 1, the next case, to be true as well. Okay? So we're going to assume sk is true and show that that forces sk plus 1 to be true. Okay? Those are the two big parts of induction. You show it's true for S1, and then you show that if sk is true, then sk plus 1 is true. And then we can conclude by induction that the statement must be true for all natural numbers. Okay? If you can show these two steps, then we can conclude. So then conclude your proof by stating something equivalent to this. You'd say something like, it follows by induction that the statement is true for all natural numbers. Okay? So something equivalent to this. It follows by induction that S sub n is true for all natural numbers n. That's the outline of every proof by induction. Do the basis step, do the inductive step, and then you make your conclusion. You say, therefore by induction, the statement is true for all natural numbers. So, give me a second to finish writing this down, and we'll discuss why this works. I'll give you a couple analogies too. Okay. So you prove that it's true for S1, when n equals 1. Okay? Then if you can prove the inductive step, this says that if it's true for any k, then the next one's true. But you already showed that S1 is true. So if S1 is true, then by this step, S2 must be true. Since S2 is true, then this forces S3 to be true. Since S3 is true, this step forces S4 to be true. So it's kind of like the book gives an analogy of dominoes. You have these statements lined up. If you can knock over the first one, S1, and then that forces the next one to fall, then they all fall. In other words, all the statements are true. Okay. So that's one way to the book's analogy as dominoes. If S1 falls, and if SK falls, then SK plus 1 falls. Therefore, we can, by induction, all the statements fall. In other words, they're all true. So another analogy I've heard is climbing a ladder. Okay, so proving a statement is true for all n is like climbing up all the rungs of a ladder. So in order to climb a ladder, you need to master two skills. You have to put your foot on the first, stand up on the first rung, and then be able to move up to another rung. So it's kind of like if you can stand on the first rung, in other words, you prove S1, and you can always move up to the next rung, then won't you always get to the top of the ladder if you can master those two skills? So that's the idea here. If you can prove the first one, and you can always prove the next one, given the previous one, then all of them are true. Okay? So let's see this, and I'm just going to give you several examples of proofs by induction. Okay? Are there any questions first? We're going. Mark.
Can you do like an S sub k minus 1 to pick up integers, or is there a version of this?
Yeah, there is. And so if you want to understand true for all natural and all integers, you still start with S1 or S of 0, but then instead of, you would prove if SK is true, then SK minus 1 is also true. The previous one was true. Then you could actually use induction to prove something that's true for all integers.
Okay.
Okay, but the proofs we're going to stick with are usually just about natural numbers. Okay. Any other questions? Okay. Let's prove, let's see, yeah, this one. So this one we'll start out with, all right? The sum of the odd numbers is n squared. Okay. Prove for all natural numbers n, 1 plus 3 plus 5 plus 2n minus 1 equals n squared. Okay. Another way of stating it using words, the sum of the first n odd integers equals n squared. Okay. Proof. We will prove this using induction. Okay, and I'm going to kind of number these parts that prove 1 and 2 to kind of model the two different steps, the basis step and the inductive step. Okay, so first we need to verify that this statement is true when n equals 1. Well, the left-hand side, I mean, we're basically saying the sum of the first odd number. The sum of the first odd number, so the left-hand side is just going to equal 1. The right-hand side will equal 1 squared. So it's trivial, right? So when n equals 1, we have 1 equals 1 squared. Clearly true. Okay? So this statement is true when n equals 1. Okay? That's the basis step. And usually the basis step is about that easy each time. You just, whatever your formula is, or inequality, or whatever, when you plug in n equals 1, you're just going to get pretty easy statement. All right, so we have the basis step. So we know the trick statement is true when n equals 1. Now we're going to do the inductive step. We're going to assume, so now assume that the statement is true for some integer k, some positive integer k. So now assume that 1 plus 3 plus 5 plus all the way up to plus 2k minus 1 equals k squared for some integer k, which is greater than 1.
Why are you assuming integers instead of natural numbers?
I could say natural number. That's 2 words instead of 1. I mean, you could say, yeah, you could say natural number greater than or equal to 1. Okay. So we're trying to show it's true for every natural number, right? So I mean, I could say natural number. So we're assuming we showed it's true for n equals 1. Now pick any integer, let k be any integer greater than or equal to 1. Any natural number greater than or equal to 1. Okay? And we're going to assume the statement is true for this k. What we have to show now in the inductive step is that the statement is true for k plus 1 when the integer is k plus 1. So this is kind of, for now, I'm going to write this in parentheses, but you don't need this down the road. It's just, when you're beginning, you kind of really need to think about, what do I need to finish, what do I need to show to be done? Okay, I need to show that this is true when k equals, when the integer is k plus 1. I assume it's true for k, and I'm going to show it's true for k plus 1. So here's what it's going to look like. So we need to show the statement is true for k plus 1. So what would that look like? It would look like this. 1 plus 3 plus 5 plus plus. Instead of k here for n, I'm going to plug in k plus 1 for n in the statement. Okay? So I take out n and replace it with k plus 1. and that has to equal k plus 1, the quantity squared. Okay? That's the inductive step. You assume it's true for k, show that it's true for k plus 1. Okay? So this is the equation we need to prove using this information. Any questions so far? Okay. So, like I said, I'm only going to put this in, here at the beginning when we do these proofs, because it can get kind of, you don't want to assume this is true. I mean, because this is what we have to show. Okay? I'm just putting it there so you know where we're going. All right. So I'm going to use this equation to get this equation. Well, look at these two equations. How does the left-hand side different from this equation to this equation? Well, it actually just has one more number. This is like the next odd number. Okay? This would be the kth odd number. This would be the k plus 1 if odd number. So really, if I take this number and add it to this side of this equation, then this left-hand side looks like the way I want it to. Okay? So what I'm going to do, I'm going to add the next odd integer. So I'm going to add 2 times k plus 1 minus 1 to both sides. So what do I have? I'm going to have 1 plus 3 plus 5 plus 2k minus 1 plus 2 times k plus 1 minus 1 equals, so this equation right here I'm adding to both sides. So I already had a k squared, and I need to add 2 times k plus 1 minus 1 to that side as well. Okay? Any questions? Okay. So it's true for, assumed it's true for k, and I just added this number to both sides of that equation. The left side is exactly what I need. The right-hand side, I'm going to be done when I can show that this stuff right here actually equals k plus 1 the quantity squared. Well, let's see. Is that true? Let's expand this. So k squared plus, let me distribute my 2. So this is plus 2k. Now you have plus 2 minus 1. That equals k squared plus 2k plus 1. And this is a trinomial that can factor, it's actually a perfect square trinomial. It actually does factor as k plus 1 times k plus 1. So that's equivalent to k plus 1 quantity squared. Let me kind of finish this up with the, that's the main idea here. I've shown that, I've really shown this equation is true now. To have the left-hand side, it does actually equal k plus 1 the quantity squared. So just to wrap it up, let me wrap up the inductive step. Then I've shown that the statement is true for k plus 1. So then 1 plus 3 plus 5 all the way up to 2 times k plus 1 minus 1. It does equal k plus 1 the quantity squared. Okay, so that finishes the inductive step. And then we can conclude the whole proof by saying, therefore, by induction, the statement is true for all n. So 1 plus 3 plus 5 up to 2n minus 1. It does equal n squared for all natural numbers n. Questions? First proof by induction, we'll give that a QED. Okay. So let's recap. We showed that the same is true for n equals 1. Then we assumed it was true for any natural number k. And we proved that if it's true for any natural number k, it's always true for the next one. Combine these two, by induction, we conclude that it must be true for all natural numbers. Okay. We proved it's true for n equals 1. This shows that, therefore, n equals 2. And since n equals 2 is true, then n equals 3 is true. Since n equals 3 is true, and so on. So they're all statements can be true. Okay. Any questions? Take a break. Take a 2-minute break.
Yes, I am. Of laughter. I got this. What do you call it? I got this. Yeah, I do.
Are you sure?
Mm-hmm. Probably.
So the next theorem, so I mentioned this earlier, that the sum of the first n natural numbers can be given by this formula, n times n plus 1 over 2. I'm going to show you 2 proofs of this, because it's kind of a classic result. So the first way I'm going to prove it is by induction. Okay. So we will prove this by induction. All right, basis step. So we gotta show this is true when n equals 1. So when n equals 1, the left hand side just equals the sum 1. But on the right hand side, if I plug in 1 for n, what do you get? You get 1 times 1 plus 1 divided by 2. So for n equals 1, we have 1 equals 1 times 1 plus 1 over 2. Well, is that true?
Yeah.
1 times 1 plus 1 is 2. So 2 divided by 2 equals 1. Okay. Which is true. Okay. All right, so we've shown the basis step. This statement is true for the natural number 1, n equals 1. Okay, now the inductive step. We're going to assume the statement is true for some natural number k. Okay, so for some integer k greater than or equal to 1, assume that 1 plus 2 plus 3 plus up to k, the sum of the first k natural numbers equals k times k plus 1 all over 2. Okay, so we're assume the statement is true for some natural number k. All right, then what do we need to show? We need to show that this forces the statement to be true for k plus 1. All right? So if I replace n with k plus 1, then the left side will go all the way up to k plus 1. 1 plus 2 plus 3 plus 3, all the way up to k plus 1. And on the right-hand side, what does it look like if I replace the n with the number k plus 1? It'll look like k plus 1 times k plus 1 plus 1 all over 2. That's what you would get if you replace n with k plus 1. Okay, so we need to show, we're trying to show that 1 plus 2 plus 3 all the way up to plus k plus 1. We want to show that this equals that. That's the rest of our inductive step. Okay, any questions? Assuming it's true for k, show that it's true for k plus 1. So I'm going to leave this off my proof. All right.
Do we take the assume or the step where we assume it's true for k, then we just add the k plus 1 on
Yeah,
each side?
and that's the way a lot of these, if there are these long equations, the left-hand side is just missing the k plus 1 in the statement that we need. So that's exactly what I do. Just like the last proof, I'm going to add k plus 1 to both sides of this equation, and then it's just a little bit of algebra to rearrange this to make it look like what we need it to look like. Okay? So then adding k plus 1 to both sides gives the equation 1 plus 2 plus 3 all the way up to plus k plus 1. That's going to equal k times k plus 1 divided by 2. Okay, the previous thing on the right hand side. But now I'm adding k plus 1. Alright? The left hand side is exactly what I need. The right hand side, I need to combine these terms to make it look like one fraction, the one fraction I need. Okay? So let's rearrange this. When you're adding fractions, you've got to get a common denominator. Okay? So k plus 1 over 2 plus 2 times k plus 1 over 2. Just getting multiplying the numerator and denominator by 2. Now they have a common denominator, I can add these two fractions. So this equals k times k plus 1 plus 2 times k plus 1 all over 2. Getting closer. Fours were not designed for proofs by induction. Alright, and continue my chain of equations, so that equals you see this? Alright, so look at the numerator. I mean, you could multiply all this stuff out and then try to factor it again. But I look at this as a factor. There's a factor by grouping here. There's two big groups, and each group has a common factor of k plus 1. There's a k times k plus 1 and a 2 times k plus 1. So I'm going to factor out a k plus 1 from both terms. Right here. So in the numerator, I can factor out a k plus 1 from both of those groups. Okay? From this group, I'm left with k. From this group, I'm left with a factor of plus 2. So it's going to be k plus 1 times k plus 2. All over 2. Any questions about that? And if you see it, let me go backwards. Like if I use distributive property, if I did k plus 1 times k, I get this. And if I did k plus 1 times 2, I get this. So just to double check. That's almost exactly what we need. It's just this does look like, you know, k plus 1 times k plus 1 plus 1 over 2, but just to be exactly, have the exact form that I need, I really need one more step, and I'm going to break this up. The k plus 2, I'm going to break it up as k plus 1 plus 1 all over 2. So now I have exactly shown that, then I've shown that 1 plus 2 plus 3 all the way up to k plus 1. I've shown that does equal k plus 1 times k plus 1 plus 1 all over 2. Okay, so I'm done with my inductive step. We showed it's true for n equals 1. We showed that if it's true for any k, then it's also true for the next k, k plus 1. Okay, so therefore, to finish up, therefore, by induction, the same is true for all n. So 1 plus 2 plus 3 plus n equals n times n plus 1 all over 2 for all natural numbers. Any questions? So these proofs by induction, you see kind of common tricks to get your statement for k to look like the statement for k plus 1. Sometimes you add a missing term on both sides. Okay. Show you some other kind of tricks here in the next group. Any questions? Go on. All right, next statement. Oh, you know what? I told you I was going to give you 2 proofs of that, didn't I? Okay, I'll give you proof that's so easy a 4th grader came up with it. Not just any 4th grader, though. It's probably the best mathematician ever in history.
Oh yeah, the counting from all the numbers.
Yeah. So this is kind of legend of Carl Gauss. That he was in elementary school, and this is like late 1700s. You know, this is math genius. I mean, he's regarded widely as one of the top 2 or 3, if not the best, mathematician of all time. And imagine his primary school teacher trying to keep him busy during math lessons. So she's like, all right, go in the corner and add up the first 100 numbers, figuring that would take him a while. Well, he comes back in like a couple minutes with a proof, and then this theorem that says, well, actually, you can actually prove that for any the sum of any numbers is this formula, right? This is supposedly in 4th grade or elementary school. So how do you do it? Okay. Well, let this sum, let S stand for this sum on the left-hand side. Okay? All right, so here's what he noticed. If you write the sum again backwards, it would look like this. N plus N minus 1 plus N minus 2 plus all the way back to down to 1. So instead of writing from 1 to n, he wrote from n to n back to 1. Now, add these two equations together. Okay, s plus s. I mean, we're trying to find a formula for s, this sum. S plus s is 2s. Now, the right-hand side, you're not going to add them up, like you wouldn't add the 1s together and the 2s together. The trick is to add these up pairwise like this. Okay, so n plus 1 is n plus 1. N minus 1 plus 2 is n plus 1. N minus 2 plus 3 is n plus 1. So you see, by adding them up pairwise, each one of these pairs is going to add up to n plus 1. So n plus 1 plus n plus 1 plus n plus 1 plus n plus 1, all the way down to plus n plus 1. So if you to get twice the sum, it's actually equivalent to just adding up n plus 1 a bunch of times. How many times am I adding up n plus 1 here? N times, right? Remember, there are n numbers here, so each one of these n numbers, each one of these n pairs contributed n plus 1. So there's n of these. So a fast way to add a number to itself n times is to use multiplication. So n plus 1, n plus 1, n plus 1, a total of n times, that's equal to n times n plus 1. And we're basically done. Twice the sum equals n times n plus 1. So then by dividing by 2, we get that the sum equals n times n plus 1 over 2. So we're done. So we showed that the sum was 1 to n. 1 plus 2 plus 3 all the way to n. We've also shown that the sum equals n times n plus 1 over 2. So, good thing. You think if your 4th grade teacher gave you that problem, you could figure it out? That way. Not me. So, that's just kind of like the legend of how good Carl Gauss is, But there's another. So this is not by induction. It's just a kind of historical proof of this result. So, all right. Any questions about that? I'm gonna need the board room when I erase this. Okay. We got. There's a joke. I had a math professor at grad school that tells a joke about Gauss. He said that Carl Gauss and his father are considered the best father-son mathematician duo in history. And most mathematicians are like, oh, I didn't know that Carl Gauss's father was a mathematician. And the joke goes, well, he's not. It's just that Carl Gauss is better than any two mathematicians put together. So. All right, so all right, the next thing I talked about was for any integer n greater than or equal to 0, 3 divides 4 to the power n minus 1. We'll prove this using induction. basis step. So now, this is actually a little bit of an extension on the natural numbers. It's the non-negative integers. So it's kind of trivially true for when n equals 0. So for n equals 0, that's the smallest n in this statement. So for n equals 0, 4n minus 1 would therefore become 4 to the 0 minus 1. Any non-zero number to the power of 0 equals 1. So 4 to the n minus 1 just becomes 0. And so 3 divides 0. You can write 0 as 3 times 0. So thus 3 divides 1 minus 1. All right. So we know that 3 divides 0. Okay. So we proved that this statement is true when n equals 0. Any integer will divide 0. Okay. All right. That's the basis step. Let's do the inductive step. So we're going to assume that the statement is true for some positive integer. Okay. So suppose 3 divides 4k minus 1 for some integer k for n equals 0. All right. So what do we need to show? This is our inductive hypothesis. We're assuming that 3 divides 4k minus 1. We're done when we've shown what?
3 divides 4k plus 1 minus 1.
Exactly. We're done when we show that 3 divides 4 to the k plus 1 minus 1. Okay, so you got to keep that in mind, right? We need to show that 3 divides 4 to the k plus 1 minus 1. Okay? All right. So suppose 3 divides 4 to the k minus 1. So what's the definition of divide means? That tells us that 4 to the power of k minus 1 equals 3 times an integer. It equals 3 times a for some integer a. So for these statements about divisibility, you're going to have this, you're going to unravel the definition of divides. 3 divides 4 to the k minus 1. That means 4 to the k minus 1 equals 3 times an integer. Somewhere in our proof, we're going to replace this quantity with this equivalent expression, 3a. Okay, somewhere down the road. All right. So what do we need to show? We need to show that 4 to the k plus 1 minus 1 is divisible by 3. So let's look at that quantity. Let's look at 4 to the k plus 1 minus 1. Okay. We know something about 4 to the power k, right? And there is a 4 to the power k here. Think about your exponent rules. 4 to the k times 4 would equal 4 to the k plus 1. You have an extra factor of 4 here than you had over here, right here. Okay? So think about this. 4 to the k plus 1, I'm going to think of that as 4 times 4 to the k. Think about that. You believe that? So this is exponent rules. All right, maybe I can break it down a little bit further. So 4 to the k plus 1, that's 4 to the k times 4 to the 1. All right, when you add exponents, you get 4, but that's the same as 4 times 4k, 4 to the k. Okay? Any questions? 4 to the power k minus 1. But here, I have 4 to the k. I'd like to put in a minus 1 right here. So this is a common trick. You add and subtract a quantity, and the equation will remain the same. Okay? So if I put in a minus 1 here, if I put a minus 1 inside this parentheses, how has this quantity changed? It's not just a minus 1, it's actually 4 times minus 1. So I've actually changed the quantity by, it's equivalent to subtracting 4, what I've just done. So to undo it, I need to add 4 to the equation. So this is one of those tricks. You know, the first time you see it, it's a trick, and then you see it over and over again. Now it's a method. Now it's like a tool that we use in mathematics. You subtract and add the same quantity. Why do you do that? So it looks like the way you want it to look. I want to remember, all I know is that 4 to the k minus 1 looks like 3 times an integer. Okay? All right. So you see we're getting pretty close. Can you feel it? This looks like this is 3 times an integer. What does this equal? 3. So this stuff definitely has a factor of 3. This stuff has a factor of 3. It looks like this is going to work out. This is going to be a multiple of 3. Okay. All right. So now I can replace this. Let me I just come over here. So this equals 4 times 3a, and then minus 1 plus 4 is plus 3. Doesn't that look like 3 times an integer? Let me factor it out. There's a factor of 3 here, there's a factor of 3 here. So factor out of 3 from both terms. I'm left with 4a here. I'm left with, I factor out this 3, I'm left with 4a. And if I factor out 3 here, I'm left with plus 1. I could, make this, equals 3b for some integer b or something. But essentially we're done. We've shown that 4 to the k plus 1 minus 1 looks like 3 times an integer. So, thus, 3 divides 4 to the k plus 1 minus 1. Okay? So we're done with the inductive step. We've shown that it's true when n equals 0. We show that if it's true for any integer, it's also true for the next one. Therefore, by induction, the statement is true for all non-negative n. Therefore, 3 divides 4 to the n minus 1 for all integers n greater than equal to 0. Any questions? Time for one more? Let's do an inequality this time. So we did 2 equations. We did one proof by division. Now, but notice that the similarity in the statements. The statements say something is true for all natural numbers. Okay? So those are the types of proofs that work out well with induction. Okay. So prove for all natural numbers n plus 3 is less than 5n squared. All right. So again, proof by induction. Basis step. So where's the basis step? On the
says water.
Yeah. Look at the equation, look at the inequality when n is 1, right? So where's the left-hand side go? So when n equals 1, we have 1 plus 3 is less than 5 times 1 squared. Everybody agrees that 4 is less than 5? Right, my college algebra students would say it's 25 on this side, but either way, it's still a true statement. So, the square, you only square the 1, and then it's 5 times 1, right? So this says 4 is less than 5, which is true. Okay. So the basic step is proven. We've shown that the statement is true when n equals 1. 2. Assume that k plus 3 is less than 5k squared for some natural number k. Okay. So what do we need to show? We're assuming it's true for some natural number k. Then we need to show it's true for k plus 1. What does that now look like? It'll look like k plus 1 plus 3 is less than 5 times k plus 1 the quantity squared. That's what we need to show. Okay? Questions? All right. So, look at this left-hand side inequality. I already know that k plus 3 is less than 5k squared. So if I add this plus 1 to the left-hand side, I can add it to the right-hand side as well, and I still have true inequality. Okay. All right. Then k plus 1 plus 3 is less than 5k squared plus 1. Now here's where inequalities, there's more freedom in the inequalities. You actually, if you keep adding positive stuff to this side, the bigger side, it's still going to be a true inequality. So, whereas an equation, to keep an equation balanced, you have to add the same quantity to both sides to keep it in an equation. For inequalities, you don't have to do that. I could keep adding positive stuff here, and this is still going to be a true inequality. Okay? So, I have the left-hand side looking the way I want it. The right-hand side does not look like 5 times the quantity k plus 1 squared. No matter how you rearrange this expression, it does not equal 5 times k plus 1 squared.
So we need to FOIL it out.
Yeah, and so this is where kind of scratch work comes in. To make your proof look nice, I would probably do a little scratch work over here. Like, let's try this. Yeah, so k plus 1, the quantity squared, well, that equals k squared plus 2k plus 1. We use the FOIL method. K plus 1 times k plus 1. And then when I distribute this, I get 5k squared plus 10k plus 5. Okay? So if I get the right-hand side to look like this, 5k squared plus 10k plus 5, then I can go backwards and get this expression.
So we need a 10k plus 4.
Yeah, we need to add 10k. Is that positive? Yeah, 10k is positive because k is a natural number. K is positive. So 10k is positive, and I need to add 4 more. So adding 4 is still positive. So note that 5k squared plus 1 is less than 5k squared plus 10k plus 5. Now, it's just kind of a note to the reader, and it should be clear that this is true because what did I add? I added 10k, which is positive, and I added 4. So 5k squared plus 1 is less than this, but this equals exactly what we wanted, right? It equals 5 times the quantity k plus 1 squared. So this is where, I mean, like, you probably wouldn't know that just from, if you work it straightforward. You kind of, this is where the kind of the behind the scenes scratch work happens, right? We want it to look like this, but that stuff equals this, and that's okay, because this is still greater than 5k squared plus 1. Okay? All right, so k plus 1 plus 3 is less than this, but this stuff is less than this, which equals what we want. Therefore, k plus 1 plus 3 is going to be less than this expression as well. And that's what we wanted. We wanted to show that the statement, if it's true for k, then we show the statement is true for k plus 1. Thus, n plus, so thus by induction, n plus 3 is less than 5n squared for all natural numbers n. And this stuff is useful when you're writing your proof, but in your finished proof, you don't include this stuff. You just let the reader think you're really smart. Oh, I guess that is true. That is true. Yeah, and that does equal that. Yeah. So, any questions? About that? All right, so these proofs, they take practice, okay? The techniques, I mean, the steps are the same, right? You have the basis step, you have the inductive step, and then you write your conclusion. Okay, it's the same, but, I mean, there's work to be done. The basis step, not so much work, but still you have to do something. This, there's different ways to show that SK implies SK plus 1. And so there's little tricks. I showed you several common tricks. For inequalities, this is nice because you don't have to always add the same thing to both sides of an inequality. I did here because I needed this side to look right, but then you can add other stuff to just the bigger side. The last one, I did this trick of adding something and subtracting it, make it look the way I want it. So there's some work to be done here showing that SK implies SK plus 1. So these proofs take practice, but hopefully the steps are clear, that you know what you're supposed to do. So we need to take some practice. We're going to continue this. I have at least one more example I want us to look at for sure on Wednesday. So we'll do some more inductions next class.